Today I'll be presenting the paper One Embedder, Any Task, Instruction Fine-Tune Embeddings. This paper was in ACL Findings 2023. What are text embeddings? Text embeddings encode words, phrases, sentences, or documents as n-dimensional vectors which we can use in various machine learning applications. We train text embedding models such that similar texts are close together when they're compared in embedding space. Text embeddings are used throughout NLP in tasks like retrieving information, clustering documents, or evaluating the output of text generation models. Prior works on text embeddings largely leverage transformer encoders. Additionally, prior works use large-scale paired text corpora. For example, a popular work called SimCSE trains their embedding model by pushing texts which entail one another close together and texts which are contradictory far apart. This is a common strategy in text embedding model training. Limitations of prior works are that they struggle to produce useful embeddings for domain-specific texts, for example, in finance or medicine. Additionally, these models can struggle to generalize to diverse embedding-based tasks. For example, maybe they're good for information retrieval, but the embeddings struggle in clustering or evaluation. This leads us to the paper One Embedder, Any Task, where the key research question is, can we teach a text embedding model to leverage domain or task-specific prompts during encoding? The paper introduces a model called Instructor, where an input text, such as "Who sings the song Love Story," is encoded alongside a prompt that tells the model what the embedding is going to be used for. This helps make the embeddings more useful for very specific tasks or domains. Let's look at another example. Suppose we wanted to encode the text, "Who is the coach of the Miami Heat?" Prior works only consider text during encoding, but Instructor makes the text encoding more task-specific by encoding it alongside a prompt that tells the model how the embedding is going to be used. Instructor is trained using a standard contrastive learning objective. The high-level goal of contrastive learning is to push the embeddings of similar pairs close together while pushing the embeddings of dissimilar pairs of text far apart. Note that in contrastive learning, we have a root text, which is paired with a positive and/or negative example. Formally, this is the objective function we aim to maximize during contrastive learning. We want the numerator to be as large as possible and the denominator to be as small as possible. In the numerator, we are telling the model to make the cosine similarity, which is S, between the root text x and the positive example y plus to be 1. In the denominator, we are seeing the sum of the cosine similarities between x and all other samples in the batch. A common way to do contrastive learning is to assume that all other samples in the batch are negative samples, as this is a way to get a large amount of negative sample training information without human annotation. However, note that Instructor does train with hard negatives, which is when there is a human annotated negative example. Please see the paper for more details. Instructor is based on the popular T5 model, which is a text-to-text transformer from Google. GTR is T5 fine-tuned for information retrieval. This is the base model used by Instructor. Instructor uses both small and large models during their evaluation. And note that the embeddings extracted from Instructor are the mean pooling of all the embeddings from the last layer of the T5 encoder. Instructor is trained using a novel aggregation of 330 datasets. Note that prior to this work, there was no contrastive learning data where each text had an associated prompt or instruction attached to it. This is one of the contributions of this work. Recall that contrastive learning data has a root text and then corresponding positive or negative pairs. Now we see that each of these texts have an associated prompt. The METI dataset was created in 2 steps. First, they found existing public datasets where there are texts and corresponding instructions for some task. They then automatically convert these into a contrastive learning format. Finally, they take existing contrastive learning datasets and they write instructions for each task. Now they have a large dataset with text pairs that each have corresponding instructions. Here are some example instructions that are used on the diverse array of evaluation tasks. The results show that Instructor produces state-of-the-art text embedding performance on the massive text embedding benchmark, billboard, and prompt retrieval. Importantly, note that Instructor XL only has 1.5 billion parameters and significantly outperforms a model with up to 5.8 billion parameters. This highlights the quality of the METI data set and the effectiveness of the training strategy. The paper does a thorough ablation study. One interesting takeaway was that automatically converting public data sets with text and instructions into contrastive learning format had a significant impact on the robustness of the model to paraphrases in the instructions. Additionally, when Instructor was evaluated on domains not seen during training, it significantly outperformed baseline approaches. This shows that Instructor works really well in new domains. In summary, Instructor produces state-of-the-art text embeddings. We see that prompt-based embeddings generalize well across a diverse set of tasks and domains and are the future of text embedding models. Thank you for watching.